Hi, it's Mr. Kane here, and now we're going to look at Rutherford's model of the atom. Rutherford was a New Zealander, and he worked here in Christchurch studying at the University of Canterbury. He was born in Nelson, top of the South Island, just south of Nelson, a place called Brightwater. Got a scholarship to university, and it's the old university in the centre of town, and his laboratory is still there. It's been set up as if he was still there, Rutherford's Den. He's honoured by being on our largest unit of currency, the $100 note, and he's honoured in other ways as well, apart from the titles and being on the note. There's a picture of him as in his Rutherford's Den at the old university, what's now known as the Arts Centre. It's open to the public. You can go and see where he worked and what he was working on there. He's honoured by having the element Rutherfordium named after him. This is a radioactive element, and he is considered to be the father of our modern nuclear age. He gave rise to this quote from him, that he's broken the machine and touched the ghost of matter. You know, considering what we can do with nuclear energy these days, the energy that's released, that's what he was talking about. And it's kind of ironic that New Zealand is a nuclear-free nation. You know, it's just not allowed to be here at all, considering that it was a New Zealander who set us on the pathway towards atomic weapons and so on. So what was going on? So early 1910, he and others were carrying out an experiment. He had set it up first, and others repeated it to confirm his work. So, for example, Geiger and Marsden, Geiger from Geiger counter fame, carried out this famous experiment, which was shooting alpha particles or helium nuclei at a piece of extremely thin gold foil. They were expecting, if the atom was like J.J. Thomson put forward, that it was the plum pudding model, positive charge with electrons scattered within it, that these nuclei would deflect or bounce back as positive charge nuclei repel positive, repelled by the positive plum pudding model atoms. They found that most of them went straight through. Only a very few didn't, went somewhere different, which surprised them greatly. So here's their setup, a deflector screen around a piece of gold foil, which they fired the alpha particles into, and then some were scattered and some went straight through. And a very few got bounced straight back. They knew they were firing alpha particles. They didn't know they're actually what we call nuclei now until after they had done the experiment and figured out what we now know to be the Rutherford model of the atom. So they had to rethink their thought of how an atom is put together, and Rutherford put forward that most of the atom's empty space, and we have a nucleus in the centre where it's a high concentration of positive charge. So here's a simple view of his experiment. We have a alpha particle emitter here, firing a beam through, most of them going straight through a piece of gold foil, a few being deflected and a few bouncing back, surrounded by a detector screen. On this side here we've got, here's the gold foil, a gold atom, and a positive nucleus in the middle. Here's a beam coming straight through, getting close to nucleus, positive repels positive, being deflected. Here's one going straight through where the electron cloud is, and it's going straight through. Here's one coming in straight to the nucleus, being deflected, bounced back, positive repels positive. So we can see that positive repels or deflects positive charges, but how does it go straight through as if it's not hitting anything? This comes down to our knowledge of the size of these particles. So we know that most of the positive charge is in the middle now. A proton is the opposite charge of an electron, so the positive repels the positive from the nucleus, and we know that it's almost 2,000 times the size of an electron. So it goes through the electron cloud as if they weren't even there. Think of yourself sitting in a rowboat being run down by an oil tanker. That's pretty disastrous for you in the rowboat. The oil tanker wouldn't notice because it's so much more massive than you are. So we now have this new sort of model of the atom. We have a highly concentrated nucleus in the middle, all the positive charges, our protons and neutrons, surrounded by a large cloud of electrons zooming around the outside of it. The atomic radius is huge compared to the nuclear radius. This is picometers, by the way, means it's really, really tiny, but the nucleus is lots smaller than the whole overall the size of the atom. Someone tried to put it into scale by saying if the atom is a Houston Astrodome, the nucleus is a marble on the 50-yard line. I wasn't familiar with this Astrodome, so I went looking for images and found this picture here of this huge football stadium, set up for baseball, set up for football, and in the centre of the here, if we put the marble on the centre here, that would be the nucleus, and the whole stadium would be the size of the atom. So the nucleus is tiny compared to the rest of the atom. Most of it's empty space, which these alpha particles could go straight through. So he put forward a model with a central nucleus, and the positive charge was all in the central nucleus. The electrons, being opposite charge, were being held in place by force of attraction, and because they are zooming around the outside, orbiting around the nucleus in a sort of a cloud of electrons around the outside of it. But the story doesn't finish there. We have a student of Rutherford, a Danish guy by the name of Niels Bohr, and in 1913 he was studying under Rutherford, and he modified Rutherford's idea that they had the electrons cloud in that, so by saying they're actually in distinct orbits, a bit like planets around the sun. Each orbit can only contain a certain set number of electrons, so they're whizzing around the outside, and we'll look more into that in another video explaining more about how these electrons are arranged and how that links to the periodic table. I hope that was helpful, and look forward to next time.